I didn't quite finish 7.5, which is what we're going to finish today. So, but all the lectures should be there. I don't necessarily upload the lectures from the test review days because there's not a worksheet to fill out. And so there's not really any way to get credit if you don't attend those sessions. So I don't bother with uploading those unless anybody asks for them. But overall, all the lectures should be there. They all say the dates of them, so you can match those dates up with the dates that we have class. All right, so let me share my screen with you. So we're, like I said, we're picking up where we left off last week. And so what we can see here is that we have our distribution with our standard deviations. So 1.495 was the mean. And then we have standard deviations in each direction. So we went down 1 standard deviation, 2 standard deviations, and 3 standard deviations. And on the other side, we went up 1 standard deviation, 2 standard deviations, and 3 standard deviations. Now remember the normal curve, if I were to draw it, we've got percentages, right, that make up these sections. So we've got 34% on each side of the mean. And then a 13.5% and 2.35%. And then the little tiny piece out here is 1.5%. Now, like I said, you don't have to memorize these percentages, but I do feel like after you keep writing them out with each one of your problems that you're doing, you start to remember them anyways. But you know, you don't have to. So part A says how many are at least 1.495. So at least 1.495 means 1.49 means greater than or equal to 1.495. So if we're looking at our table, 1.495 is the mean. So we're talking about all the stuff that's that way. So I want you to think about what that would be as a quantity if we're discussing 1,000 parts, and send me your guess in a direct message. Sam's freaking out. I don't know if you can hear him meowing through the video. He's just running around, I guess, being a wild boy. So when we think about the mean is the middle, right? It is the average. So it splits our data in half. So we've got the half that's less than the mean, and we've got the half that's greater than the mean. So when we're saying how many are at least 1.495? 1.495 is the mean. So at least, and if we were to again look at our, if I were to shade all of this in, that's 50% of our data. And therefore, if we have 1,000 parts and I say how many are going to fit that, it's going to be 0.5 times 1,000 or 500. We would have 500 parts. Where is this? Where it's just a certain part, right? It's got that mean diameter. So there's 500 of them that would fit that quantifier, right? At least 1.495. So it's that half, the greater half. So part B says, how many are between 1.485 and 1.50? Oh. Okay, so part B says, how many are between 1.485, which is right here, and 1.50, which is right here. So if I look at the amounts that are there, excuse me, so from 1.485 down to 1.50, I've got 1.49 and 1.495. So this is 34%, this is 34%, and this is 13.5%. So we're going to add those up. And when I add those, I get 81.5%, right? So when I take 1,000 and I multiply it by 0.815, because I'm finding 81%, 81.5% of 1,000, I'm multiplying it, giving me 815 parts. So part C says, how many are between 1.480 and 1.505? So looking at our drawing, we want to go from 1.480, which is right here, right, up to 1.505, which is right here. So if we look at the percents that are between those vertical marks, we've got 2.35% plus 13.5% plus 34% plus 34% plus 13.5%. So when I add those up, I get 97.35%. So I'm going to take 1,000 and I'm going to multiply by 0.9735, which gives us 973. Oops. 0.5 parts, approximately, right? Because we have the half a part. All right, so the last question for this one says, how many are between 1.500 and 1.505? So 1.500, I just don't have the extra zero there. So what's up at the top? Okay, so 1.500 and 1.505 is 1.500 is right here, 1.505 is here. So that's 13.5%. So if you're having a hard time with, so we've got 13.5%, right? And so we're saying what portion of the 1,000 is 13.5%. So we've got 0.135 times 1,000. But if you're having a hard time remembering to turn it into a decimal number from that percentage number, The alternative way to solve this is to say 13.5 out of 100 is equal to X out of 1,000, right? You could set up a proportion and solve it that way too. And the only nice thing about doing it that way is that it keeps you from forgetting to go from that percent number, the 13.5%, into a decimal number, meaning converting it, because that process is a little confusing because we already have a decimal point in the 13.5%, right? So solving it using a proportion is an option too. So again, with the proportions, you would cross multiply. So we can see that 13.5 times 1,000 equals 100x. And then we would divide by 100. And we would still get 135 as our answer. Okay. So the last piece of this is margin of error. So margin of error, we have this formula. So it's z times the square root of p times 1 minus p all over n. So what do these letters represent? Well, we've got z is called the z-score. And so we are just barely getting into statistics with this. We're sort of giving you just enough information to be dangerous in terms of like, we're not getting into what z-scores are. Z-scores actually have to do with standard deviations when you're dealing with not a normal distribution, but we're not getting into that. We're just saying, okay, here are 3 z-scores that you're gonna have that we're gonna use. We're not gonna get too deep into this. P is the percentage. And so that term will make more sense when we get into a practice problem, and N is your sample size. So when you're looking at this formula, you're going to take P, and this is going to be as a decimal number. And you're going to multiply it by 1 minus P. Then you will take that value, divide by your sample size. Then you will take the square root, and then you will multiply by your z-score. So the z-score has to do with our confidence in the answer being accurate. So a 99% confidence would give us a z-score of 2.58. 95% is a z-score of 1.96, and 90% is 1.645. We are giving you those values because that's what you're going to use. We're not going to deviate from this. They're not like, I'm not going to suddenly give you new z-scores later on. These are the 3 that we are going to use. These are the ones you're going to use in your homework. And so I don't want you to think that okay, so it says a survey is conducted of 800 people, meaning N equals 800. If 45% responded that they were in favor of a certain new law, find the margin of error for 95% confidence, meaning we are 95% confident that the real answer is 45% plus or minus the margin of error. So I've already identified what your values are here, meaning we're saying that 45% of the people, meaning P is equal to 0.45 with a sample size of 800, and we're looking for the margin of error for 95% confidence, meaning we're going to use a z-score of 1.96. So if P is equal to 0.45, then 1 minus P equals 1 minus 0.45 or 0.55. So we want to put these values into our formula. So we've got a z-score of 1.96. And then we've got times the square root And then on the numerator, we've got 0.45 times 0.55 over n, which is 800. So there's a lot of pieces that we have to do here in order to get the, to do an order of operation, okay? So what do we need to do first? What do we think? Because if we had a graphing calculator, we can put this all in, but we don't all have that, right? So what can we use instead? How can we calculate this instead? So yeah, we can multiply first, meaning multiply 0.45 times 0.55. Which gives us 2.475. So we still have 1.96 times the square root. Now, instead of writing 0.45 times 0.55 on the top, we can replace that with 0.2475. And that's over the 800. So from here, we can divide by 800. So here's the problem with doing this by hand, each a little piece by hand. When I take 2.475 and I divide by 800, I get 3.09375 e to the negative fourth, meaning times 10 to the negative fourth, okay? So if you don't have a graphing calculator, that's perfectly fine. What can we use instead so that we are being as accurate as possible? So there's a free website called Desmos, DESMOS.com. Have I showed you guys this website before? So I'm going to share my screen with you so you can see what I'm doing. So it's Desmos.com, right? And so I press enter. It's going to take me to the website. And this comes as a free app on your cell phone as well, or you can, again, just use it straight on the internet. You don't have to log in. I know on the left-hand side, it says log in or sign up. That's just if you wanted to save your stuff, you don't have to do that. So we're just going to use the graphing calculator. And again, the reason why I'm showing you how to do this is because if you start intermittently rounding, your answers are going to be off. And so what we want to do here, so again, if I take 0.2475 and I divide it by 800, you can see we get that really tiny number, okay? So in here, we can tell it to do stuff. So I used my arrow key to get in front of it. So I'm gonna do a parenthesis, and I can do a parenthesis on the end. So how do I tell it to take the square root? Well, I'm gonna say SQRT, and it's going to tell it to take the square root of that. Now, it's not underneath the square root symbol, is it? So in order to get it to do that first, we would have had to type that in first. So another way that you can get that option to come up is down here in this lower left-hand corner, it says show keyboard. We bring that up, you can see here you've got your square root key. So I would press square root, which puts that in first. And then I would put 0.2475. And I would hit the division key and then 800. The thing that's nice about it is it's calculating it in real time. You can see this, how this number here, the equal sign changed as I was changing it. The last piece we need to do is we need to multiply this by the 1.96. So I'm going to do 1.96 in front of it and press the times sign so that it will multiply. I don't even have to press enter. It's already giving me the answer here in the box, right? So when I multiply this together, I get 0.03447. And I'm just going to leave it there. I know it's a really big decimal number, but we're going to leave it there. Your last stage is to convert this to a percent, right? So we convert it to a percent. And remember, to convert a decimal number to a percent, you move your decimal point 2 times to the right, giving us 3.447% would be our margin of error. So how does that apply to like, what does that mean? So you can see this statement here where it says the answer is 45% plus or minus the margin of error, meaning we would do 45% minus 3.447 and 45% plus 3.447. And this is not part of your answer. I'm just showing you how we would talk about this in terms of statistics. The answer was just that 3.447%. That is your margin of error. So adding and subtracting these, I get 41.553 and 48.447. So what that means is that if we want to have, if there's a margin of error with a 95% confidence, what that means, and let me show you what I'm, let me go back to the screen so I can show you what I'm talking about. So what that means, I've got this interval, right? So so if I wanted a 95% confidence, that means in real life, from 41.553% up to 48.477% of those 800 people are in favor. We can't say it's exactly 45% because we have to allow for a margin of error. Okay, that's what the margin of error means. It means that your answer is somewhere within there and that we are 95% confident that this survey is accurate. Okay. So obviously we want to be as confident as possible. So we want the smallest margin of error, but we have tolerances that are allowed. And so why do you even need to know this? What does this have to do with it? This has to do with medical testing, right? And so when they do medical testing in terms of like a new drug or something like that, they report their confidence, right, that with a margin of error for the results for the test. And so that's where that is coming in. I don't expect you to have to do this in real life. However, we want you to know so that if you're reading something, you understand what they're talking about. Okay. So, I want to do one more example before I get into number 2, because number 2 is really confusing. So let's do one more example, and I'm going to pull this from your textbook. Hold on. Oh, that's right. Your textbook doesn't have margin of error in it. I forgot about that. All right, let me do one thing. Hold on. I'm going to do one of your homework problems with you, like from the worksheet. Okay, so number 1 on your worksheet says you ask 400 ground squirrels if they like to watch CNN. Why not, right? They could like it. You never know. And 72% responded yes. What is the margin of error if you use a 95% confidence? So remember, margin of error is equal to Z times the square root of P times 1 minus P over our quantity N, and 95% has a Z-score equal to 1.96. So send me your margin of error to 3 decimal places after you convert it to a percent, okay? So again, just to remember, if we identify our pieces in here, the 400, that is our N value, right? And 72, that is our percent. So that means P is equal to 0.72. So 1 minus P is equal to 1 minus 0.72 or 0.28. So now we got to put the stuff in, right? So we have a z-score of 1.96. And we're going to multiply that by the square root of 0.72 times 0.28 divided by 400. So we have to be really careful again how we are putting this stuff in, right? We have to make sure that we're not rounding off our values. So we've got 0.72 times 0.28 in the numerator, then divide by 400, then take the square root, and then multiply by 1.96. And that's where I'm saying use Desmos or a graphing calculator or something so that you are not coming up with rounded values. So if we look at Desmos here, we're going to do the square root, or excuse me, we're going to do 1.96 times, and then the square root. And then in our numerator, and so in order to indicate that we want it to be numerator, we're going to do a parenthesis of 0.72 times 0.28 in parenthesis. And then we're going to press division, and then we're going to do 400. And so I'll press enter, and I get 0.044001. And I told you to take it out 4 decimal places. So now to convert this to a percent, we multiply by 100, giving us 4.4001. Say 4 or 3 decimal places, I forget. Either way, it's basically 4.4%, right? So questions about this process? So I think one of the biggest hangups is remembering that what do we get from 1 minus P, right? How that relates to the initial percentage, and relating those two things together. So again, we're just having to pick out our pieces of information and then build off from there. So if we go back to our worksheet, what happens when we have the margin of error? We want some of the starting information, okay? So this is a really important thing to think about, because it's like, okay, well, I know I only want, and so in number 2, it's saying in the past, a survey was conducted to which 75% of people responded in favor of a new law. A new survey is going to be conducted. And the goal is to have a margin of error of 3%. How many people will need to be surveyed for a 99% confidence? So that's where in the past, they're like, okay, we did the survey, we got this amount. We want to redo that survey, but how many people do we actually have to talk to in order to have that margin of error and that confidence? And so that's a really common problem that gets solved for in statistics. So if we think about our formula for margin of error, it's Z times the square root of P times 1 minus P over N. So what do we know? Okay, well, we know that our percentage is 75%, which we're going to put in as 0.75. We know our margin of error is 0.00 or 0.03, excuse me. And we know we want to have a z-score of 2.58, right, for the 99% confidence. The piece that we're missing is N. Okay, so let's plug in what we have and we'll go from there. So we have 0.03 that we put in for a margin of error. The Z value is 2.58, and that's being multiplied by our square root of 0.75 times 0.25. Again, where did that 0.25 come from? It came from 1 minus P And we are dividing that by an n value that we don't know. So how do we even get to n? There's all these things in the way, right? So let's think about how we break it down. Looking at this, I've got 2.58 being multiplied by something, right? So eventually we're trying to get to the n. In order to get to the n, we have to unpack what we've got going on here. Meaning, I'm going to divide both sides by 2.58. Doing this cancels this out on the left-hand side. And 0.03 divided by 2.58 gives us a really big decimal. So for the purpose of this, I'm going to leave it as 0.03 divided by 2.58. Again, the reason I'm not converting it to a decimal is because it is a decimal that has 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places. That's a big number. Again, it would give us opportunities for error with rounding. And so I'm going to leave it as it is. So right now I have an equation that has a square root symbol. And I want to undo that because I need to get to the variable which is inside the square root. So to undo that, I need to square both sides. Squaring a square root undoes it. So squaring this left-hand side, 0.03, is going to give us 0.0009. And squaring 2.58 gives us 6.6564. So what can I do next? What do we think? So multiply, how would we multiply? Like, what are we thinking we want to multiply? So we can multiply the proportion, right? So cross multiplication. I like the suggestion of first multiplying 0.75 times 0.25, but then, yes, we want to multiply inner proportion. So let's simplify the numerator in the fraction on the right-hand side. Oops, forgetting my... And then from here, yeah, we just solve our proportion. We're going to cross multiply. And of course, I'm running out of room. So let's copy this work. We'll take it to the next page. Okay, so we're going to cross multiply, meaning we're going to take n times 0.009 equals 6.6564 times 0.1875. Sorry, when I drew my little arrow, I got rid of the decimal point, right? So we'll simplify the right-hand side. And I know this is a lot of steps, a lot of decimals, right? Well, we want to hold them, we want to keep them, because if we round at any point in here, we're going to end up having an answer that's off. And we get 1,386.75, which is going to be approximately equal to 1,387 people, because we can't talk to 3/4 of a person, right? Even if they're missing a leg, they're still a whole person, right? You can't say that that's a 3/4 of a person. That's not nice. And the other thing, one of the things I want to warn you with here, if you want a specific percent, right, for your confidence, even if, let's say I had 1,386.2, I would still round up, because rounding down is going to give us a lower confidence amount. So rounding up is just going to increase our confidence. And so you would want to round up to the next whole person with these problems, okay? So what do we think about that one?
So on the homework, for these type of problems, when it says margin of error to be within plus/minus like 3%, do you just use like 0.03?
Yes.
Okay, like the plus and minus doesn't matter.
No.
Okay,
it's cool. Just indicating that. So again, our margin of error, I see what you're talking about. So like number 4, when it's talking about a survey of deer.
Yeah.
So all they're saying is the margin of error is 0.03, because when we use plus or minus, we're saying that the real range is actually 3% below up to 3% above. And so we just report that as a plus or minus 3%.
Okay, gotcha. Thank you.
But yeah, you just say margin error is 0.03. That's all they're indicating. All right. So before I move forward into 8.1, we have time to talk about questions about 7.4, 7.5. Did anybody get a chance to look at the homework for that section, or look at the normal distribution worksheet or the margin of error worksheet and have questions that they have about that content?
I put a question mark by 19 and 20 on 7.4, but I don't remember what it was about. So one sec.
Okay.
And for number 14 on 7.5, so to find the upper, is that just the 100.2? That's just plus the 1.8, or is it plus 1.8, 1.8? If that makes sense. Is it 2 1.8?
Talking about
for the upper and the lower? Yeah, I just did.
So use the mean and standard deviation to determine the upper and lower control limits for its normal glucose control. Right, because we have our table, because we're using that to answer 11 through 16.
Yeah.
And so we've got our our upper and lower control has to do with the 3 standard deviations. So it's 3 standard deviations above and 3 standard deviations below.
Oh, it's 3 of them. Okay, gotcha.
Yeah.
Okay.
Because when we say upper and lower control, what that means is, remember, anything outside of 3 standard deviations is considered an outlier. And so we want them to be within those 3 standard deviations.
Okay, gotcha. Okay. Thank you.
Yeah.
So for 20, I put the mean would increase by 2%, but the standard deviation would not change. Is that right?
That is a good question. You're talking about,
On 7.4.
right. So what happens if we actually do the math for it? So if we think about, we've got salaries of 3,500, 3,600, 3,700, right? And they're all getting a 0.2% raise. Oh geez, what happened? Come on, come back. There we go. So the mean for this was this one, right? Because if we have 3 values, the mean is going to be the middle value, right? If they're evenly dispersed, right? Or each, it's the 100 is the difference. So if I add those up, divide by 3, I get the 3,600. So the mean for the new is, you're right, 2% more. So then what about the standard deviation? Does it impact the standard deviation? So if we find the standard deviation for this, so the standard deviation for the first set is 100. And the standard deviation for the second set is 102. So it is increasing the standard deviation by 2% as well. So it's being constant since we're changing the percent for all of it. It increases the mean by 2% and it increases the standard deviation by 2%.
Okay, gotcha. Because it was similar to 19, but since it was a percent, it could just kind of confused me. But
Yeah, exactly.
Okay, thank you.
So in those ones, honestly, that's where I say calculate it out, right? The data is small enough that you can find the mean, you can find the standard deviation for the 2 sets, and then you can you can then compare and, come to a conclusion. I
Okay,
personally
thank you.
like to do that instead of, they're trying to see what is your overall global understanding of changes in mean as you change the data. But we haven't worked with enough data, honestly, to have those conclusions that we can just pull out of thin air. So that's where I would say, actually calculate it, figure out what's happening, and that will help you to come to the conclusion of how this is being impacted.
Okay, thank you.
Yeah. Any other homework questions before we move forward? All right, I'm just going to grab our 8.1 stuff. And so chapter 8, we're completely changing directions. So chapter 7 was all about statistics, and we're going to end the class. So chapter 8 is our last chapter of the class. This is week 13. We are teaching new material this week and next week, and then the rest of it is going to be review for the 4th test and then for the final. So we are quickly approaching the end of the semester, which is crazy to think. But chapter 8, we pivot to talking about logarithms. And the reason we talk about logarithms is so that we can talk about the pH scale. And so we're just doing a very, very thin amount of this, meaning we're not getting real deep into it. So when we're dealing with logs, I want you to think of powers of 10, because logarithms are related to powers of 10. And so the first thing I want to talk about is, let's look at our trends with powers of 10. So if I have the number 1,000, how do I get 1,000? By raising 10 to an exponent. So if we think about multiplying 10 times 10, 10 times 10 equals 100. And 10 times 10 times 10 equals 1,000, correct? So when we multiply values together, we can use exponents to represent that. So 10 times 10 times 10 is really 10 to the third. So the number 1,000 is 10 to the third. The number 100, right? To get 100, I do 10 times 10, which is 10 squared. And now how do I get 10 to just be itself? I'm not multiplying it by anything. But if I want to use exponents to represent this, we say that that's 10 to the first. And then things get weird. So if we think about our pattern, right? Let's think what's happening with our exponents. So we went from 10 to the third, down to 10 to the second, down to the 10 to the first. We're subtracting one each time, right? So that using that pattern would give us 10 to the 0. And that's true because any number to the 0 power equals 1. When you raise any number to the 0 power, you will get 1. If I raise 3,721 to the 0 power, it will equal 1. Now from here, we start to get into negative exponents. So 0.1 is the same as 1 over 10. And 1 over 10 can be represented with 10 to the negative first. Which means 0.01 is 1 over 100 or 10 to the negative second. And 0.001 is 1 over 1,000 or 10 to the negative third. So small numbers have negative exponents. And we talked about this a little bit, remember, when we were dealing with unit conversion with the metric system and using powers of 10 there. And then larger numbers are going to have positive exponents. So how does this relate to logarithms? So in the equation y equals b to the x, the base b is raised to the power x to give the value of y. This means that y is a function of the value of x. If we know the value y and the value of b and need to find x, we use logarithms to solve for x. When the base b is 10, it's called a common logarithm. And so on your calculator, when you see that log key, and if you don't see log, you may see 10 to the x and then it's related to that key. That's because your calculator is assuming that it's a base 10 logarithm or a common logarithm, okay? So why do we use logarithms? Again, one of the big things that you will be dealing with, pH scales. So you will see these in chemistry as well. It has to do with the acidity of a solution. If we talk about, and I'm going to get into pH more, a pH of 7 is considered neutral because it's a 0 to 14 scale, and pure water has a pH of 7. Blood, like human blood, the pH is very close to 7 because the majority of our blood is made up of water. And so then on either side, you have acidic or basic values, and it's very common to think, oh, well, if it's down on the basic side, it's not acidic at all. Well, that's not true. It's just the way that they describe it. Values that are on either end of the spectrum will still eat through something, right? They'll still be really caustic and will cause damage. Radioactive decay rates, half-lives, and then so decay rates and half-lives, that's really the place that we see that is that they talk about carbon dating. So that has to do with knowing the half-life of carbon, and that's related to using logarithms and exponential equations. That's our current dating system. And then earthquakes. So I grew up in California, specifically in the Bay Area, and so earthquakes were a very common part of my life. And but it's not like I knew what they meant. I just knew the number. And so that has to do with the system, right? Alexis, I never spent a lot of time in Santa Cruz, unfortunately, because it's so far south. Pretty much like Monterey was as south as I got. We went a couple of times down to Santa Cruz, but unfortunately I didn't get to spend a lot of time. It's beautiful there. And then finally, the last one has to do with sound and decibels. And then the decibel system is all based upon the lowest audible sound, and then it relates to that with what we hear. And so why do we care? What are we doing with this? So instead of getting really deep into it, we're going to think about how do we analyze these, right? So we've got this statement, log 1,000. First of all, that is an operation, not a piece of wood, right? You're going to see the word log. I want you to think powers of 10. So when we look at this, we know 10 to the third equals 1,000. So the log of 1,000 is equal to 3. So we're always relating it back to powers of 10 that you know. So it might be helpful for you to keep that table on the front, or that list on the front page handy, and you might even want to add to it, right? So if you do 10 to the fourth, that's going to be 10,000, 10 to the fifth, 100,000, and so forth, and then moving down below, and that will help you to analyze these. So looking at that table on the first page, think about number 1. I want you to find log of 0.1, I want you to give me a guess of what you think that equals to based upon the powers of 10 that we already talked about. So we know that 10 to the negative 1 is equal to 0.1, right? So what does that tell us? That means that log of 0.1 is equal to negative 1. So when you're evaluating this, all you would have to list is the negative 1. We don't need the other part. So I want you to try 3 and 4, and then we will talk about number 5. So for number 3, be kind of confusing, right? We're saying log 1, but what we want to ask ourselves is 10 to the first equals what? Or not 10 to the first, I apologize. 10 to what value equals 1? Well, we know 10 to the 0 equals 1. Therefore, log of 1 is equal to 0. In number 4, I have 4 zeros, okay? So this method only works for powers of 10 that are positive, meaning you can count the number of zeros and that would be the exponent on the power of 10. So we know that 10 to the 4th is equal to 10,000. Therefore, log of 10,000 is equal to 4. So number 5, you might be tempted to say, oh, well, the number's 2 or the number's -2, right? So if we try those, 10 to the 2nd gives us 100 and 10 to the -2nd gives us 0.01. Neither of which are going to give us -100, right? And that is because this is not possible. Even if I took -10 and rose it to the 2nd power, I would still get a positive 100 because we cannot take the log of a negative number. So that's one where we have these guesses that should make sense in our brain, right? Like, well, clearly I'm trying to get to -100. If I use -10, that'll get us there, and it won't, because when we square it, it becomes a positive number. So again, number 5 is not possible because we can't take the log of a negative number. Okay, we did a lot today. I'm going to stop us there and we'll pick these notes back up on no, not Wednesday, that's tomorrow. We're not seeing each other tomorrow, on Thursday. And then we will talk about it then. Again, if you didn't have a chance to look over 7.4, 7.5, normal distribution, margin of error, that whole kit and caboodle, I can answer questions on Thursday with that stuff. Okay, so feel free to look through that again. And if you have questions, we can touch on those then. There is an assignment already posted for 8.1. You have a ton of time to get it done. So if you want to look at it, feel free. If not, no big deal. I know you had your quiz due yesterday. If you didn't get a chance to get it in today. I haven't even looked at them yet. So we'll just pretend I didn't see it and it was always there, right? So just let's get those in. And then, yeah, you've got homework due on Wednesday, right? 7.4, 7.5. And then margin of error and normal distribution isn't due until Friday. So we've got a little time. Any questions for me before we go? All right. Well, I hope you all have a good day. I will get this lecture uploaded as soon as I can. As you know, with good old YouTube, it takes a little while to process. So it'll be later today. But I hope you all have a good day and I will see you later. Bye, everyone.